Hi guys, BuildZoid here, and welcome to another video that nobody's probably going to watch, because that's how it goes anytime I pull out the oscilloscope. I mean, it's not currently on screen, but you can already see that that's the passive probe. That's a piece of, well, there's a piece of coax going to the back of the card. There's this thing, and this thing is the thing that the video is actually about. So that right there is a little current sense amplifier module. It's based around this chip right here from Texas Instruments, which is the INA180, which is a current sense amplifier. Basically what this does is it takes the voltage drop across a shunt resistor, and depending on which flavor you have, it either multiplies it by 20 or 50 or 100 or 200, and then outputs that relative to ground. So, yeah. Anyway, the reason why I have one of these, actually I have 10 of these chips now, but I've built only one module so far, is because what these allow you to do is you can measure the voltage drop across a shunt resistor with a single channel of the oscilloscope, whereas otherwise you'd have to do it with two separate channels, because the shunt will have like 12 volts on one side, 11.995 volts on the other, and so if you try to use a single passive probe to measure across that, you're going to be shorting 12 volts to ground through your oscilloscope, which is bad for the oscilloscope. So yeah, you can't do that. With this, however, you know, the output of the amplifier is relative to ground, so you can just hook up the 10x, like you can hook up the passive probe to the amplifier, and all is good. So yeah, this is a close-up of what the actual assembled module looks like. I'm not entirely happy with how this one turned out. I'm toying with the idea of maybe using battery power on a few of them, just because the way this one runs is it basically takes 12 volts from the system that it's hooked up to, and then the 5-volt linear regulator converts that to, well, 5 volts, which is then used by the INA180. And then this connector over here is what the passive probe from the oscilloscope plugs into. Now, the reason I'm not happy with this is because we have this ground connection to the system that it's connected to. And that means that, and the thing is, like, technically the oscilloscope is plugged into the same power strip that the computer's plugged into, but there's going to be a difference in the ground voltage between the two of them. So ideally, I'd actually not, like, this ground connection right here, I'd ideally not have that. Or more, like, ideally this would be running off of the, like, this would be only connected to the ground of the oscilloscope instead of the ground of both the oscilloscope and the system that it's like measuring a shunt resistor in. Alternatively, I could just run it off of a battery, and that's just, sorts out the, like, power supply and ground issue. Or I could run it off of, like, the USB port of the oscilloscope, but I don't really like that idea because USB cables are kind of bulky and they get in the way. So yeah, I think I'll probably experiment with running this off of, like, a small battery, because I don't really need like, there are some limitations on, like, what kind of measurements you can take depending on what kind of power supply you run this chip off of. But basically, like, it'll run on anything from, where is it? It'll run on anything from, like, 2.7 to, like, 5.5 volts. So I'm thinking, like, a tiny little battery should be able to run this, because it doesn't really pull much current. And so it should be possible to run it off of, like, each module just has its own little battery, and then I don't have to worry about, like, the grounding thing, which is potentially why right now I have a measurement on the oscilloscope that's, like, negative when it really shouldn't be negative. But yeah, so this is not finished, but in its current form, it is already capable of doing something that I think is incredibly cool. Which is, so originally these are meant to, you know, amplify the voltage drop across a shunt resistor, which is great and all, but, like, you can also amplify the voltage drop across a power plane, right? And so what we can do is we can actually take a very, very fast measurement of the voltage drop across the power plane, because the INA180, like, this thing has a 350 kilohertz bandwidth. which isn't actually that high. But from my test, like from me messing around with it so far, it seems more than fast enough to catch basically any transient on a GPU. Like, I've not, because the thing is, I have the piece of coax hooked up to the V-core, and the scope, I have it unlocked to 100 megahertz bandwidth. I've not seen any like significant core voltage event that doesn't correspond to a event on the that measured by the INA180. So basically, what's really cool with this is you can now, like, instead of just looking at the voltage regulation of a GPU and kind of, you know, having to assume here the current, like, here's probably a load insertion transient, here's probably a load release transient, instead of having to make those assumptions based on how the voltage is behaving, well, we can now look at the oscilloscope and see exactly what kind of transient caused what event. The only issue is that since we are measuring across a power plane, I have no idea what the resistance of the power plane is, and therefore we have no idea how much actual current is flowing. Because the whole reason why you use a shunt resistor is because if you know the resistance of the resistor and you know the voltage drop across it, you can calculate the current flowing through the resistor. If you don't know the resistance of the resistor, you can tell if the current flow is like increasing or decreasing, so you can track the transients, but you won't actually know what the, like, how much current is actually flowing. You can tell if it's more or less, but you can't tell how much. So we can track transients with the current setup, and that's really cool. Because yeah, I think it's really cool. Because I wanted to be able to just like sort of show the current draw transients to explain why like a GPU is just incredibly noisy, and so now we can do that. So I'm pretty excited about that. Anyway, let's bring up the oscilloscope, and yeah, this right here, the minimum value being read as like minus 30 millivolts, I think that's entirely a grounding problem. So that's why I'm thinking about messing around with having some of these run off of battery power, because I shouldn't be seeing minus 30 millivolts. Or maybe I should read the documentation in it with a bit more, like, a bit more, but I think it's probably mostly down to the fact that, like, because this has been an issue with passive probes in the oscilloscope forever. Is just like, yeah, like the scope's ground is at a very slightly different potential than like the ground on a GPU. So yeah, which makes sense because there's potentially a lot of current flowing through the ground planes of the GPU. But anyway, where was I? Right, let's take a look at some transients. So we're just going to be running some 3D Mark because it's the best. It's my favorite benchmark. Actually, we're going to be running Firestrike because Firestrike's my favorite benchmark. Anyway, and I guess we'll take a look at what it looks like when you don't, like, you know, what you typically see when a GPU is doing its GPU things. So we're just going to run graphics test 1. And we're going to run this at 1080p, and this is just going to be a horrible noisy mess because GPUs are very noisy. Not really much more to it than that. The pink line is the output of the current sense amplifier, and the yellow line is the output of the core voltage. So, as you can see, compared to idle, our purple line is now, you know, much higher most of the time, but it is also very, very noisy. We zoom in a bit, and I'm going to set the trigger somewhere. Oh, that's not the trigger, that's the horizontal scale. So if we stop it here, well, you can pretty clearly see why we have this voltage undershoot here, because you can see that our current draw, right, like we have this little valley where there's not a lot of current draw, and then it ramps up, and so our voltage falls off a cliff. I should also note that this GPU's VRM is kind of garbage, which I'm not too surprised by, but annoyed. So yeah, anyway, if we keep going along, you can see other transients. Like here we have a load release straight into a load insertion again. So you get the big voltage upward spike and then undershoot immediately afterwards. Because yeah, GPUs just like GPUs are basically a nightmare scenario for power delivery. Like, yeah, like they're really, really bad. So that's why if you measure a GPU with an oscilloscope, you basically get something that looks like completely random noise, because GPUs pull current at pretty much random, like random amounts of current, basically random time periods, constantly. Like there really isn't any, like, unless you have something like VSync running, and the GPU is like inserting idle time, you don't really get a very steady current draw from a GPU, because that's just not what GPUs do. Anyway, now we're going to run some Firestrike, but with VSync. And this, actually, do I want to run it full screen, or do I want to not? Let's window it, because I did this test with it windowed. So we're going to window it so that, like, I don't get surprised by it behaving differently. Now, the thing about running windowed VSync is that it actually syncs to like 30 FPS or something. Like, it glitches out. It's not 60. But anyway, so I'm going to zoom us out to like a lot. So here you can see how, yeah, so it's currently VSyncing to 30 FPS. And you can really see how, you know, like VSync is basically inserting a pause between each frame render to sort of sync 30 FPS. Anyway, we're going to want to zoom in on some of this a bit. And so here you can see like the whole like, you know, we have this whole idle section right here, and then the GPU renders a frame, and you can really see now, like, rendering a single frame is just like gibberish, basically. Like, during a single frame render, the GPU transitions from, like, you know, basically like maximum current draw right here, and a few other points where like the current draw is really high, and there's a few points where we have, like, you know, relatively like sustained high current draw over here, some sustained high current draw over here. Incidentally, the timescale we're at right now is 1 millisecond per division. So like this current spike over here, or, well, yeah, this like sustained level of current draw over here, that's like half a millisecond that is held for. Similar with like that, and quite a few of these other ones. But anyway, if we keep zooming in on this, and unfortunately my oscilloscope has a bug when I'm very zoomed in, that sometimes you get random spikes. Hopefully we don't run into that. You know what? I maybe shouldn't have zoomed in that early. Maybe scrolled to the beginning and then zoomed in. So let's zoom in. So you have the initial ramp up, right? Because like here we're at idle. Or, well, oh, and it's glitching out. Man, why does my scope do that? Right? Like that wasn't there in the capture. And then it just... Oh, I think I see another two of those. That is so annoying. Anyway, if we zoom in on this section, right, so here you can sort of see the initial startup, and there's really not, like, the start of the frame is actually, like, relatively mild. I mean, we do still get some pretty nasty undershoot, especially when it ramps up to whatever this is. So we get quite a bit of undershoot right there. Then as you keep going along, you know, the power draw actually is relatively mild right here. Well, mild. It's pretty high. It's pretty high. Keep going along. And like you have a lot of like a lot of bits where you just have like random current draw spikes or dips. Which makes sense, but yeah, it's kind of like there are CPU workloads that behave like this as well. Anything heavily memory bottlenecked has a tendency to be extremely spiky. And well, GPUs are probably kind of the definition of memory bottlenecked, right? Like, look at the 6900 XT with its infinity cache. Anyway, over here we get a really nice, like, clean load insertion transient because our current draw spikes way up and we get this massive undershoot over here. And then we get the, you know, the typical GPU thing of like, oh, stop doing whatever you're doing. Current draw drops to like nothing. Then ramp right back up to 100% load, which triggers a whole bunch of undershoot, right? Like here, right, like this during this like sustained level of current draw, our core voltage is around, is sitting around 1.2 volts ish. When that transient hits, the voltage drops all the way down, like below 1.1 volts. Like there's like 90 millivolts, maybe 100 millivolts of undershoot. And then once the VRM finally recovers, we're up at around like 1.18, because this admittedly is a high level of current draw, and AMD GPUs do have some amount of DC load line on them, as in like intentional V-droop to sort of minimize the difference between the bottom of the undershoot and the sustained current draw. Because here's the thing, like there's not really much point pulling the voltage all the way back up to where it's supposed to be if, you know, your chip has crashed because for a fraction of a microsecond it was getting 1.1 volts when actually it needed 1.2, right? Like that's sort of why we have load line, is because there's just not much point, because like your voltage regulator is never going to produce a straight line, and so sort of fighting physics for your to try maintain like the voltage perfectly steady is just not worth it. And so shoving in more voltage, like if your voltage is off by this much, and then you pull the voltage back up, like you're just adding extra heat output without gaining extra stability. Now, interestingly enough, GPUs generally tolerate some amount of undershoot compared to CPUs. Like typically the CPU voltage regulator spec is designed so that there's very little undershoot, whereas I've not really encountered any, well, that's not entirely true. There are some GPUs that have incredibly good voltage regulation, but most of them don't. Like, a lot of GPUs will tolerate, like, surprising amounts of, like, come with surprising amounts of undershoot from the factory. And by undershoot, I mean the spike downwards. I don't mean the fact that, like, the load voltage gets pulled down based on output current, because that's V-droop, which is different. Anyway, then we get a load release transient, which creates that nasty spike upwards. Luckily, nasty upward spikes can't cause blue screens, so I don't really care about them. Though it is worth noting that this card's voltage regulation is really bad. Yeah, I've not measured many RX 580s, but in the grand scheme of AMD GPUs, this thing is terrible. This RX 580, which I don't think is really that surprising. Because you know, it does use a 3-phase voltage controller with a bunch of doublers to get a 6-phase V-core VRM. So I wasn't exactly expecting this to be like the pinnacle of voltage regulation on RX 580 GPUs, but I'm still disappointed because I wasn't really, like, I usually hope for a peak-to-peak value on a GPU of like 200-ish millivolts. Also, the data's corrupted, so we can't really take that measurement. But if we run more Firestrike without VSync, yeah, I'll kill VSync, disable windowed mode. We're going to go back up to 1080p. So, like, I normally hope for around 200 millivolts on GPUs. Like, I've measured some GPUs that are under 200 millivolts, which is occasionally, like, very low power consumption cards, or very well-designed voltage regulators. That's sort of the only two types of GPUs that get under 200 millivolts, which is like the reference Fury X PCB which has a very good output filter and is just a, you know, straight up 6-phase with relatively low inductance. That VRM, I think, normally is typically below 200 millivolts peak to peak. Oh yeah, this RX 580, you know, it maxed out a peak-to-peak value of 350, and, you know, it was averaging around 300, like over 300, which is not the worst thing I've ever measured. There are NVIDIA GPUs that do worse, but as far as AMD GPUs go, this is really bad. Like, I'm surprised at how bad it is. Now, the good news is that does mean we get, like, the transients are a bit easier to see, but it's also not like I couldn't just zoom in the oscilloscope more if the voltage regulation was a bit better. Anyway, that's basically it for this video. Yeah, like, this is just a really cool sort of measuring capability that I have now. I'm not sure what I'm going to use it for yet. Like, I wanted to be able to do this for ages. Obviously, you can also use it to measure the current draw of a GPU from the like PCIe power connectors with, you know, very, very quickly, right? So like if you're trying to catch how much transient loading the GPU is putting on the PSU, it can be used for that. That's sort of the original reason why I was interested in this, because technically you can get like some very expensive current probes for oscilloscopes that'll also do this kind of thing, but they're, like I said, very expensive. These INA180s are actually really cheap. I think I got 10 of them for like £2 a piece, something like that. They're not like the cheapest chips ever, but they're also not super expensive. So yeah, I bought a bunch of them, and yeah, now I can take measurements like this, which is really, really cool. Also, I can use it on CPUs. With CPUs, it'll be, I think, more interesting, because with motherboards, it's really easy to change how much V-droop you have. So it'll be really interesting to basically, or I don't know that it'll be that interesting. Like, this is the thing I've been struggling with, is like, because here's the thing, like, by looking at what the voltage, like the core voltage is doing, you can pretty much guess what kind of transient just occurred, right? Like, if I take channel 3 off the screen, oh, it won't let me. Can I, oh, there we go. So yeah, if I take channel 3 off the screen and I just zoom in on some random part of the core voltage, like, I can probably guess what happened. Here, like these upward spikes, that's obviously load release transients. And if I bring channel 3 in, oh yeah, exactly. Like, you can see the current draw, like, dropped in, like, literally in correlation with all of those spikes. Like, the part I'm a bit disappointed by is, like, it's basically a mirror image of what the core voltage is doing, right? So to some extent, it's like if you look at the core voltage, assuming that the voltage regulator doesn't have some kind of weird ringing issue or something, you can pretty much guess what caused what spike, because, like, that's how that works. So that's kind of the slightly disappointing part for me. I guess it would be more interesting if I was actually monitoring, or, well, I don't know that it would be more interesting. It would also be interesting to just monitor, like, input current draw, right? To see if, like, hey, is this GPU potentially going to trip over current protection on your power supply? Because that's sort of the intended purpose of this. Because with this, I have no idea how much current is actually being drawn. Like, I can see that the current draw is going up and down, but again, don't know how much current it's actually pulling right now. Whereas if you're using shunt resistors on the 12-volt side of the GPU, then yeah, you can tell exactly, like, well, you'd also need to take a voltage measurement, and my scope potentially will run out of channels if I try to do that for too many shunts at the same time. But yeah, like, with that setup, you can actually sort of tell, hey, like, the GPU is potentially going to trip over current protection or something. So I guess I could hook up shunt resistors to, like, Vega GPUs and stuff. That might be kind of interesting to look at with this. But personally, I'm more interested in looking at well, I don't know if I'm more interested in looking at the power plane. Like, this is just a measurement capability that I've kind of wanted for ages, and now that I have it and I'm looking at the graphs, I'm like, this is doing exactly what I thought it was doing, and now I'm disappointed. In a sort of, like, I was hoping to get some new insight into what is going on, and it's just like, well, no, now what I've always suspected is exactly what is happening. So I'm kind of underwhelmed, I guess. Yeah, but it's still pretty cool, and I am going to assemble all the other ones. I guess it would be interesting to use it with, like, various, well, no. Yeah, like, I'm not sure what to do with this. Like, it is cool. Because, like, the part I care about, like, I know a lot of people might care about the transient loading on the 12-volt side because it's like, oh, that might shut down your power supply. But personally, I couldn't care less, because, like, my approach to PSU purchases is just, like, get a really big one, and then accidentally shut it down anyway with your multi-GPU setup, and then get another really big one. So well, the bigger issue is like I don't do GPU reviews in large quantities. So like this would be really useful on something like an RTX 3090 or a 3090 Ti or a 6900 XT on something like that. But yeah, I don't have any of those. So yeah, that's kind of the main issue with it for me. Is just like it makes, you know, like it makes some pretty neat squiggly lines, but they are squiggly lines that I was completely expecting to see. So yeah, that. Oh, it could be kind of like, well, that's the thing is just like I don't really have a lot of GPUs that I'm like wondering what their peak current draw is. Right, like an RTX 3090 or something, then it would be interesting. But this is an RX 580, and the highest power consumption card I have is probably a Vega. So it's just like, eh. You know, like, who cares about Vega? Also, Vega's power plane is going to be, like, actually... Also, yeah, I'm also not entirely sure how you would go about setting this up on a Vega's power plane, because it's that weird... Like, I'm not sure what would be the best place to measure from. I don't know. So yeah, anyway, I wanted to show this off, because, like, while I am a bit disappointed that it just sort of shows exactly what I thought it would, it is still kind of neat, I guess. Yeah, I don't know, leave a comment with, like, ideas for what I can use this for that would be, like, interesting to normal people. Because to me, it was just like, oh yeah, this works exactly as I expected it to, and it shows me exactly what I thought it would, and I'm bored now. So, so that's kind of that. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And then I also have a Bandcamp where I post like industrial metal background noise type stuff. So you might want to check that out. Actually, any of those, like there's links to the Patreon, Teespring, Bandcamp down in the description. If you want to check any of them out, it would be much appreciated, because that is how I fund things like this right here. So, yeah. Anyway, that's it for the video. Thanks for watching, and goodbye.